Welcome to the special pre-Thanksgiving Science seminar today. It's our great pleasure to have Professor Sanjay Shakkottai as our speaker today. Sanjay is the professor at the University of Texas at Austin. He has appointments with both PC and the CS department. And I know he's also the director for the new Center for Generative AI. It's a campus-wide computing resource, and I already have heard a lot of interesting research coming from that center. Sanjay have received a lot of awards from NF's Career Award to IEEE Fellow, and also the Bennett's Prize from the IEEE Communication Society. He has done a wide range of research topics, from wireless communication networks to reinforcement learning to general machine learning, and more recently, generative AI. I have been following his work since I was a PhD student, and I always find his research very interesting and inspiring. And today he's going to tell us about his recent work on diffusion model. Sanjay, the floor is yours.
Thank you so much for the invitation and for hosting me, and thank you all for coming the day before Thanksgiving. I honestly thought the only person who would be here would be Chauvin because she invited me and was stuck with it. So, thank you all for that. So I'm going to be talking about discrete diffusion models, but before that, I want to start with some continuous models and then these diffusion discrete models. This is work primarily by my graduate student, Litu Raud. He worked with me in Constantine. Constantine Karamanis is my colleague at UT, who's a co-author on all these works. And this is also in close collaboration with teams both at Google DeepMind and at Google. At DeepMind, it's Nathaniel Ruiz, who was with Imagine, and Abhishek Kumar. And within Google with Yujua, Andreas, Yasam, and Srivatsan, Ira Kavalmakar, Schleiserman, and Vincent Chuk, who are in the Pixel team and Google Shopping teams. So, with that background, I start. Yes, good. All right. So let's look at sort of the evolution of. First, let's think about image generation models and look at the evolution. So today, these image generation models are the state of the art for high resolution images at scale. In the last several years, starting from sort of the open model by Stable Diffusion with the 1 billion parameter model, this really sparked a lot of research worldwide because it's an open model. And today, the state-of-the-art models are Flux and Stability AI SB 3.5, which are flow models, which are closely connected with sort of diffusion-type models. In some sense, they're all mathematically very similar objects, but they're scaled up now, and they're the foundation model of choice for a wide range of downstream tasks, starting from text-guided image editing, or image denoising, or in-painting. So as an example, what I mean by in-painting is you've got this image with some part missing, that's the bright blue stuff, and then you ask it to complete it, it's able to generate this background. Or motion deblur, which is you get this image from a camera, which is moving, and then you want to deblur it to get a high-resolution image. Or even image personalization, which is give a style, say this melting rose gold style for an image of a dog. And maybe you also give one image of a dog, your dog, say. And you want to combine these and generate an image of this dog in this style. And this is what I mean by image personalization. So these are some applications. And you want to do these kinds of things quickly, meaning within 30 seconds to a minute on a standard A100 class GPU. So that's really the goal. So these are all essentially posterior sampling problems in high dimensions. You've got a base generative model, which is a diffusion model, which is able to generate, it just learned the universe of images. And these are usually text guided. So it's been learned to align text and images. But then what you do is to give some quote unquote measurements. The word measurement I'm using in a very general sense. It could be one measurement, which is like this image of this dog, or it could be this style as a measurement, saying extract the style of this and generate, and the content of this and generate this image. So this is your measurement, and you want to do a posterior sample using a base to generate any of these kinds of things. And as I said, diffusion models are the state of the art for images today. And these are essentially based on the underlying technology of continuous diffusion, which is roughly smoothly noise an image and then learn how to progressively denoise it in latent space as a base generative model and do all sorts of things on top of it. Before I sort of move to discrete diffusion models, I want to talk about so for any of these kinds of things, there's a huge global community who have been working on these types of things. So I just want to talk about a few of things we have been involved in. Couple of things. So we have worked closely with various Google groups and how, in particular, algorithms for stylizing, image editing, as well as inversion and editing with flow models in a lightweight edge platform such as a Pixel phone have been productionized now on Google Pixel, on the tablet, on the YouTube platforms. Many of these things are in production. So I'll give you an example of the kinds of things we are able to do now at scale. One example is the following. So you give this image, which is a reference image, and you give one image of a style, this particular content of this dog, and ask to compose these together, and you want to generate an image that combines these things. This is an example of what we're able to do now at high resolution. There's full HD quality image, and roughly in about 30 seconds. To sort of get a sense of the scale of these things, these images are all 1024 by 1024, meaning in 3 colors, which means the ambient dimension is 3 million if you vectorize this. You can go down to a latent space of order of tens of thousands of dimensions. And that's the space in which you're doing sampling and editing and things. And what RB modulation, it basically views these problems as the posterior sampling as an optimal control problem. And then you test time generate a controller, essentially which guides the image to sample from the correct posterior. Something that RB modulation is able to do is actually to do these kinds of diverse layers, meaning it's not trying to extract the boundary of this and actually generate the image in the same style. You can see that it's basically extracting quote unquote what content means and is able to generate these kinds of things. Or they're able to we are able to generate novel styles. For example, this is a neon graffiti style image. This is a glowing style image. And you're asked to, say, generate tiger that combines these styles, that interpolates between these styles. So this is a style which doesn't exist in any training data set. But we are able to sort of generate these kinds of new styles as well. These are a few examples of the kinds of things we've been able to do with RP modulation. Another really interesting problem is free image editing. So if you have got a lightweight platform like a edge device where any gradient computation for image editing is super expensive, can you come up with a flow-based algorithm which just sort of in some smooth manner able to generate high-resolution images? And this is something we have been able to do. An example being you give this image of this cat and ask, I want to convert a sleeping silver cat sculpture. What you want to do is to flow this image, the cat, noise, do some noise editing and flow it forward. You can sort of view this as a form of counterfactual sampling, and I'm not going to talk about too much about that here, but this is in our recent paper called RF. So, but foundation underlying all these things is the usual continuous diffusion, which is you start from an image, you progressively add Gaussian noise a little bit at a time, smoothly, till you get pure Gaussian noise, and then you progressively learn to denoise each step. And once you've learned that, then if you start with any new noise sample and use this denoiser iteratively, you're hopefully going to get an image. This is the underlying technology. The bulk of today's talk is not about this, but there are early indications that a shift is starting to occur, and there's a lot of interest in something called discrete diffusion instead of these continuous denoising models. And what some of you know diffusions, perhaps others have not played with it. So what exactly is a discrete diffusion? It's essentially the following. First, it's tokenize and diffuse. So say, let's look at a text string, a cat is playing with a dog. Or another example, which I'll keep in mind in parallel, is this image of this bird. Okay? So in which case, for text, you need some dictionary to break this up into tokens, words in the vocabulary, and then convert this string into a bunch of integers. Say, let's say for concreteness, let's say you're using a dictionary of about 50,000 words. Okay? Then this tokenizer would simply break this up into a sequence, okay, where each element in the sequence is simply an integer between 1 and 50,000 comes from the word in the dictionary. And I've just drawn this here as a grid to represent. It's not a grid, it's really a string, but you can draw it however you want. And just because we are doing images and text, we are drawing it as a gradient. Okay? So this could be the number. If it's A is 300, this could be 300. This could be the word cat, which means it's 483, and so on. So each one of these colors is simply an integer between 1 and 50,000 corresponding to a word. Okay? But if it's an image, then what you would do is to break it up into tiny blocks. This tokenizer would be it could be a vector quantizer or something like that. We'll map it to a dictionary. And then again, each patch would map something of 1 of 10,000 words in this dictionary. And again, you have exactly the same representation. So finally, once you move to the later, you take whatever the content, the actual data, and represent it as a sequence of integers, whether it's image or text. And then the noising process is fundamentally different from what we looked at before. I'll talk about one specific noising thing. In discrete models, there are more other noising models. I'll just talk about something called mask noising, okay? Which is you take any particular token at some random time, you blank it. You introduce a new word in the dictionary called mask. Okay? This is not one of the actual words. It's an extra word. It's just erase, essentially. And then what you do is you just erase it. So, for example, this orange one got erased in the first step. This red one remains. It got erased at some point. And eventually, you end up over time steps to get all these. Okay? Forward noising process. And the first process is trying to predict what each mask could be. So in this place, maybe you try to predict this in red. Maybe at this point, this is missing. You predict this is green, and so on, until you finally get all unmasked. So unlike a continuous diffusion model, in this at least, at some point, each block is completely erased, and you go to the absorbing state of all masks, and denoiser or a demasker is iteratively trying to figure out a flip into a word till you get the word sequence back. So why do people care about this discrete diffusion model? Well, first is it's faster inference potentially, meaning because the world is fundamentally discrete, perhaps you can take far fewer denoising steps in the iteration to actually get to an all unmasked state. The second is the way this thing works. So let's look at this particular block. Okay? Yeah, I just called it a red block. But what is it really? The way it's represented internally, let's say the vocabulary is 50,000 words, is simply a one-hot encoding over the 50,000 dimension vector. So if it's red, say this one, say corresponds to the number 300, say, then this will be represented as 0, 0, 0, 0, up to 299, 1 at 300, and 0 and 0. Okay? So it's just a vector, one-hot encoder for each one of them. Which means this comes to 1. I could actually generalize it and think of this as some categorical distribution over the alpha. So I can do soft prediction. I think it's red could be represented as 0.9 at that point. And maybe it could be something else, could be some other problem. So what you are actually maintaining for each one could be potentially a distribution. Okay? And because there's a categorical distribution per token, this provides finer control, and you can decouple different parts of the image or text and guide each. And this decoupling allows sort of much finer posterior sampling. So meaning, I give you a particular image and say unbutton the third one. Okay, it's a very, very local kind of thing you want a posterior sample for. And this categorical distribution gives you much finer control to do those kinds of things. So these are some advantages. There are two major problems with discrete. The first is the reason it's fast is because things jump abruptly. But the reason it's hard is that things jump abruptly. Same reason. which is that there's a lack of smoothness. When you start from a particular token, and it disappears, it completely is wiped out. There's no hint of it vanishing gradually like noisy, like in the continuous diffusion. Okay, and this sudden information loss, especially with an important word. Let's look at the sentence: a cat is playing with a dog. If the word cat and dogs disappear at some point, you lost a lot of context. In a smooth model, okay, maybe it becomes a blurry cat. I don't know what that means in language, but there's some way to do that. Things could blur out much smoother. There's much more signal. This is huge loss, and that's a problem. The second issue is there's no gradient guidance. Discrete state spaces means that you cannot use sort of a score to guide your process in some latent space to actually do posterior sampling. Okay, because the notion of what a gradient means is not at all clear in this setting. And this lack of gradient actually makes posterior sampling at scale really hard. And so the current state in literature is there's a lot of excitement of these types of models, but there is still a big performance gap for text in terms of worst perplexity or generated quality with respect to autoregressive models. And for images, where posterior sampling is sort of critical, these are not the lack of gradient guidance means that the current methods are just not scalable at the high resolution. This is where we are today. So today's talk is going to be about a simple idea called anchoring, which we have developed. And instead of giving you the definition, I'll tell you intuitively what it is. Look at the sentence: a cat is playing with a dog. Okay. Suppose that you are given a hint about this and somebody is willing to reveal a couple of words. Which of these words will be most useful to you to try to figure out the rest of the sentence? If I told you the word A and S, it's not that useful for figuring this out. But if I told you cat and dog, it's much more useful in trying to infill everything else. Essentially, what are those words you can condition on such that there's a substantial reduction in the conditional entropy of the remaining tokens? Okay. So or another way of thinking about it is, if you think that there's a multi-level graphical model, what do you think are the root nodes, which if you can figure out, you get conditional independence across the leaves and much easier to predict those things. Another example. This is from the GSM-HK dataset. Janet's duck lays 16 eggs per day. She eats 3 for breakfast each morning and bakes muffins for her friends every day with 4. And it goes on and asks finally, how much in dollars does she make every day at the farmer's market? I have to give you a few words here. If I tell you that it's about breakfast and muffins and farmer's market and even they're not as important as the numbers 16, 3, 4, and 2. That's really critical for solving this problem. So those are what we would call anchors here. Okay? Or in the image setting. Now we have explicitly seen the tokens here. If you are revealed a few of these background tokens, intuitively it seems like it's less useful than if I give you some of the foreground tokens. So even a few of them is going to help decode the rest. So these are what anchors are. So what we have done is to redevelop essentially the denoising models to take into account such anchoring both in the language setting and the image setting. So in the language setting, we have developed anchor diffusion language model, which is what I'm going to talk about today, which is the first diffusion language model that at its scale generates better human-like tests than an AR model. And essentially, anchoring provides the smoothness. I told you that there's information loss, sudden information loss of masking. So anchoring essentially gives a certain notion of information smoothness that's going to help the process. The other problem I talked about is lack of gradient guidance. I'm not going to talk about it very much today, so I'll spend a few minutes just telling you what it does. Okay. This is a discrete diffusion model for images, not for. So if you give it a prompt, high quality image. Okay, let us look at the way this image is being generated. To look at it, first the easy tokens are being generated, which is just the empty foreground is what is generated. And then it is sort of going from outwards and then it's trying to fill in the rest. So this is basically what it does. So the way these diffusion models work is you have to unmask tokens at each time. And the easy ones are those which are high confidence. And those are typically the background tokens. So this is how things work. But now if I ask you, here's a blurry image of a duck. Use this to generate a high resolution version of the uh, same bird. What anchor diffusion model does is, if you look at the thing, it's taking a longer time to do anything. That's already started. But when it starts, it's starting from the foreground. It's realizing that those are the more important things. And once you do that, it's able to decode many other things much faster. Okay. So this has allowed test training-free optimization. And the way this is done is using anchoring through sort of a gradient-like guidance in discrete embedding space. I'm not going to talk very much about it here, but I'm happy to chat about it offline. Today, I want to talk about anchoring. So for a language model. So let's get to sort of diffusion language models more broadly. Over the last several years, and in particular this year, diffusion models have really taken off in terms of industry impact and various groups who are working on this. One example was Gemini diffusion that was released recently. Another is Mercury from Inception Labs. Basically, they were able to show that diffusion models, because of their parallel generation, are able to generate things much faster in code generation. For example, going down from 75 iterations for an autoregressive model to just 14 iterations in a diffusion model. And diffusion models, I'll talk about it a little bit more carefully in a few minutes, allow parallel decoding, and so it can manage sort of long-range connections much better in the autoregressive models, and therefore can potentially be more accurate. And so these are some examples. Lara is another big open model people have used in the research and the industry. In terms of the history of these diffusion language models, so the idea of these kinds of diffusion language models goes back to the 2015 paper by Soldenstein et al. But at scale, the first model here was D3PM. It's a mass diffusion model for automotive. Then there's a lot of interest in 2022. You can see the number of papers there. By the time, about 2023 as well, you can see sort of the scale of interest in terms of sort of big models is roughly the same. But by 2024, the timeline has changed. Every 6 months, you're seeing the number of interesting models come out at the same scale as over the year. And in 2025, you can see even more. Now the timeline has moved to one every 3 months. So this is just to illustrate that there are lots and lots of groups who are interested in these models for a reason that it has certain promise, but still it's nowhere near production scale compared to AR models. Okay. Again, we talked about discrete language, why discrete diffusion previously. Now, why diffusion language models? Because again, diffusion models can do tokens in parallel, not sequentially. There's no causal ordering like an autoregressive model. You're just dealing with the whole thing. Everything is masked. Whatever you think you want unmasked first, you can do so. There's no reason to go from left to right. And therefore, if you can, especially if you can sort of flip multiple masks to words at a time, you can speed things up. Autoregressive models, by construction, will generate one token at a time. Each forward pass generates one token. Here, potentially could generate several tokens in one shot. Okay, which is immediately a multi-speed. The second is flexible editing, which is it natively handles infilling, rewriting, and so on. If I want to condition on something towards the end of a sentence or somewhere in the middle and want to be consistent with the beginning, you do this in autoregressive by sort of instruction tuning or SFT or something like that. But these things could natively do those kinds of things potentially. Okay. The third, which I'll talk about in somewhat more detail later, is nonlinear reasoning. Because you're not sticking to a left to right order, you could potentially have planning. You could say that I want to get to these kinds of landmarks, sort of figure out those landmarks sort of somewhere downstream, and then diffuse to make sure that happens. So again, there are advantages of reasoning with diffusion language models. And the landscape of diffusion language models today, roughly in these 5 categories. One, the mainstreams right now are these masked models, which I give you an example of. You tokenize, represent your text as just a sequence of integers, and then randomly mask till you get to all mask, and then tricon mask. Okay? D3PM, SED, MD4, MDLM, and LADA are all examples of these kinds of models. The second class of models are something called uniform noising models. Instead of masking, you could just flip it to some other word. Okay. So the model starts from your sentence. So if the 17th thing is an A, you could flip it to with or something else. You randomly flip to some other word and then randomly re-flip. So it flips over the it's a random walk over the vocabulary in a forward noising process, and then you try to reverse it. Examples being SED, GGM, SED is out of Stanford, GGM from Google, DDPD, QO, PLM. There are a whole bunch of these models around it. There are also mixed noise. You can combine these things, combine multiple strategies for more robust training. There are also hybrid models which are starting to get popular, which are if you say you want to generate 4K tokens, well, maybe you will diffuse at the level of maybe 256 tokens and then auto-regress over those blocks. Okay. And I suspect eventually these are the kinds of architectures this will go, things will evolve to in a few years. When diffusion models, if it's working at scale at 2K or so, will generate those blocks and then auto-regress much, much longer sequences over those blocks. So it's something to be looking out for as we evolve in the next couple of years. And finally, you could actually do continuous diffusion. Okay, meaning the last step, you could actually do continuous diffusion with an embedding layer, which will take these discrete, these Gaussian, whatever vectors in the continuous space, and lift it back to a discrete space. And people have tried that as well. We'll show some performance of these things. Today, mass diffusion models are empirically the best performing. Does it mean that next year that's going to be? I'm not so sure, but this is state of the art today. Okay. So this is actually exciting because, yes.
So why do you think uniform noise diffusion that looks actually closer to the continuous diffusion if I change continuously don't work at them?
So I'm not sure if everyone heard his question. He was asking why don't uniform look sort of like continuous? Why is mask preferred? Because both uniform and mask have a huge disadvantage, which is when you flip, there is no notion of locality in English. Is A closer to with than tan? That such a question is meaningless. Noising in the continuous world, has meaning. If I take a picture and blur it, it's still close to it. I can figure out it's close. When I noise things in the discrete world, there is no semantic structure there. So you may as well as go to full mask as opposed to randomly flip to anything else. Okay. So this is one issue. Second issue, the uniform has a problem that in a mask diffusion model, when it has been noised because there's a special character mask that appears there. So already when you see it, this is no longer the truth. In the uniform model, that is a problem. I suppose I give you a sentence which I say some of them have been randomly flipped. Now, can you tell me which have been flipped and which haven't? Is a non-trivial question. So in that sense, it's actually worse than a mask diffusion model. Okay, it loses the information smoothness, and it also loses the signal that what has been noised and what. But it does have an advantage that it's a recurrent model. You can re-noise and re-noise again and again, and so it allows you to correct errors. So that has an advantage. But now you see it's a thing why mask is generally better, but that doesn't mean to say uniform might not become better. But it's very, very different from continuous diffusion because there is no structure or closeness when you noise things. Okay. All right. So this is the state of sort of the models today. And so let's just get into mass diffusion model once more. So this is the DTPM, MDLM, or MD4, which are all sort of similar. Essentially, some implementation details are different and scales are different, but they are similar ideas. So this is what you start with. Let's say the sentence you have right now is A, mask is mask with mask mask. What a mass diffusion model then does is use a denoising transformer with bidirectional attention. And then what it does is predicts the next one. Importantly, let's say the predicting was the playing was the one that was decoded. It will not, unlike a standard AR transformer, this can depend on all the unmasked words. So A, is, and with are all unmasked. So basically, the next word that's flipped could use everything that's unflipped. There's no notion of before and after. Potentially, it could flip multiple things, not just playing. It could similarly decide to unflip this as well. In this example, it hasn't, but it could. Okay. This is, and in the process, this is essentially this is the way it flows. As I said earlier, it starts from all tokens, all masks. We try to reverse it. The forward process is a independent per token noising process, which is what is written here. It's product form across L tokens. L is the collection of tokens. For each token, ZL, let's call this the Lth position, this pink one. Okay, you want to figure out if you want to figure out what is the probability that it's actually some value at this point in time. Well, it's one of two things. It's either a mask or it is what it was original. So it's essentially a categorical distribution based on two things. It's either what it started with some probability alpha t, or with 1 minus alpha t mask. So this is the forward process. It's a very simple forward process. It's an absorbing thing. Uniform is more complicated to write. You can write it too, but it's just more messy. And the reverse process is really interesting thing. How is it parameterized, the reverse process? So let's go back here for a second. What one would think as a first cut idea is the following. If I have this, let me try to predict this in the following way. The forward process is Q. This is Q of ZT. So the way this is written, this forward process here is written as Q of ZT given X, where X is this whole thing. But you could rewrite this as a Markov chain. It's time inhomogeneous Markov chain. But you could rewrite this as a time inhomogeneous Markov chain of Q of ZT given ZS, ZS given Z1, something one step back. You could write it as a chain like that. And then you could say, hey, reverse, we'll just look at the reverse posterior. So I'm at ZT, I want to predict CS given ZT. Let's look at Q of CS given ZT and try to learn that function. Okay? That's something one could attempt to do. It just basically just reverse this Markov chain. Okay? That's not what is done. The way it's actually done is a nice parameterization. And this parameterization follows from the elbow. I'm not going to get into sort of why exactly the parameterization is, but I'll give you the inclusion of this. So I'm at CT, and I want to figure out the distribution for CS. That's my learned distribution. So P theta is the learned distribution. Theta is the parameterization for the network. It's trying to predict a time S given the entire vector as a time. Some things to observe in this location. For me, in this talk at least, always S equal to T minus 1. It's one time step. So let's just keep that in mind. And we are going to try to predict the Lth token, a particular token, given the entire vector. So in this picture, given this red, this blue, this orange, and these things, I want to say predict this particular pin token's distribution. The parameterization it's going to follow is the following. It says that if a token is not masked, it's already been unflipped, then it continues to remain the same. Okay? That's the top one. So once I unflip, I will never remask it, at least in this base model. You could think of remasking models as well, VMDLM and all that. But here, once it's unmasked, it remains unmasked. If it is masked, let's look at this one. Then the way it does this is the following. It says, look at the true posteriors of this quantity, given this and this. Okay. So again, let me repeat. I want to figure out the posterior at this point, given both this and this. If I know both endpoints, then I know that this one must be either this one or masked. That's what this has to be. It has to be one of this state or this state. And so it's a category. So the prediction network in a mask diffusion model does not predict the next step. It always predicts what it thinks the ground truth is. Wherever I am, it will try to predict this as a soft distribution and use that to figure out what this is. That's the parameterization used in mask diffusion. Okay? So what you're trying to learn is X theta L of CT, which is given CT, this entire matrix. What is this? What is the distribution? What's the soft distribution on this? It's a categorical distribution of 50,000. Okay, so this is the mask diffusion model, and this can be trained using standard cross entropy and the ergo laws. So hopefully you get a sense of how sort of a discrete diffusion model works. So all this was just sort of a tutorial. None of this is our work. It is all sort of in literature by these. And as I said, the key problems here are first empirically performance gap. It's worse perplexity and lower generated text quality. The second issue is that the important token problem, which is that random masking could actually drop important rich words, such as nouns, verbs. In the sentence, a dog is playing with a cat. A cat and dog sort of early in the diffusion process, you see that it's very, very hard now to sort of figure out what, even if I know A and this, to figure out the rest of the sentence is much harder. So what we developed is something called the anchored diffusion language model, which has the idea is essentially the following. Again, you start. So I'll show the inference pipeline, then the training pipeline, then some theoretical results, and then empirical results. That's sort of the flow. So first, the inference pipeline. So you got A mask is mask with mask, just as before. So what we create, first construct is an anchor transformer. The anchor transformer does not predict tokens. It predicts soft tokens or distributions. It predicts essentially soft tokens are for dictionary length vectors, but it's not a token, it's a distribution. For each one, it predicts what it thinks is are important words. Okay? For example, let's look at this. A is already decoded, so its distribution is speaking at A itself, okay, because it knows it already. For this, suppose it figures out that this is likely to be a cat, okay, then its distribution is going to peak at cat with some other things as well. For this one, it has no clue what it is, so its distribution is going to be roughly uniform or whatever. It's a flat distribution, and so on. So what the first stage transformer is doing, it's just predicting a bunch of distribution. And then a denoising transformer ignores everything down here and instead takes what the anchor outputs are, figure out what the next one decoding should be. So in particular, suppose playing is decoded here. Previously, with the standard mask diffusion model, A is and which will be used to decode playing. Irrespective of the fact, the anchor transformer, anchored model, it's also using the fact that somewhere in the sentence thinks there are likely to be cat and dog. And this, even though it's not unmasked, it's anchoring on these words to actually decode this word playing. So, this summarizes what I just talked about right now. So I'll skip it. The 3 points: unmasked tokens speak at their true values. Anchor predictions for important tokens have a skewed distribution on the important words. Others are flat, but denoiser uses, whether it's decoded or not, it uses all these anchor predictions to do the next step decode. So one way of thinking about it is anchoring simply creates a latent reasoning space. That's what you can think of. Despite things not decoded, this is what I reason to actually decode it. The question is, how do you train this model? So to illustrate though what the implications of the inference are, so we empirically observe indeed that anchoring has 2 main advantages. It unmasks keywords first and unmasks many tokens in parallel. So at times, so in a 4096 or 4096 97 step diffusion, let's look at MDLM, which is standard mask diffusion model on the on my, I guess I'm facing you on my right. Look at the kinds of words that have been decoded. It's but in other words, they're easy words, they're high confidence words, but not really useful. Okay? Whereas at the same time, the kinds of words an anchoring one has decoded are things like responded and security and trusting and secretly. It seems somehow more important for the sentence it's going to construct. And so this is an example of what anchoring does. How do you train this? Okay. So as I said, there are 2 transformers. There are anchor transformer and denoising transformer. What we've done is basically previously there was 1 transformer. In the examples we talked about, there were 18 layers. Here, there's a 12-layer transformer and there's a 6-layer transformer. So in terms of total number of parameters, exactly the same. It's just organized differently. 12 of the layers are the anchor and 6 of the layers are the denoiser. It's sort of a single 18 layer. And what you do is to break it up so that you produce these soft tokens here, which I need to decode. Typically, what you do is to supervise thought. It's as though in a deep network, you're going in some middle layer, which is a sort of a representation layer, and you're basically supervising that as well, in addition to supervising at the end, at the output during training. And what I mean by that is the following. When you get a sequence, so I got a training sequence, say a cat is playing with a dog. We pre-process it to extract a small number of anchors. Okay, cat and dog for this one. In the number example, the digits. So in general, given any string, we have tried various different ways of constructing anchors. One is simply low frequency words, TF-IDF. Okay, just any word which appears less than 5 times, let's call it an anchor, some threshold. Okay, so this pre-processing step takes your sequence X, appends to get sequence Y, which is the anchor sequence. Okay, it is math reasoning, numbers are anchors. In logical reasoning, for example, cross QA and so on, verbs and nouns as anchors. You could also use another language model to say, what do you think are important in this, and do such a pre-processing, which is something we have played with as well. So, since the key thing is, these are tokens whose inclusion as conditional variables is substantial reduction the conditional entropy of the remaining. You want a small number of such things. Yes.
To go back to the previous slides. So when you have this anchor transformer predicting the anchor point, so this using another prediction hat to.
I'm going to show you next slide exactly. Good. So I've now told you what anchor words are. Okay. Now how do you use this? And this is the training pattern. Okay. So on what you know are the anchors, you put cross entropy loss here. There is no loss on these ones. On this side, for those that are decoded, it's fine. It's decoded. For anything that is masked, you put a cross entropy. You know what the sequence is. So they say this thing is a cat is playing with a dog, and this is the output of your transformer. Just like in any normal thing, you put a cross entropy law between this and this. What extra thing we're doing is a second cross entropy law on this reasoning space, but only on the anchor tokens, what we think is anchor position. The rest, there is no supervision. Okay? And then you train this end-to-end. And in terms of the size of this model, it's exactly the same. It is just that in the intermediate layer, they are giving a certain other type of supervision. You can think of it as a supervised thought, essentially. Okay? And this is you have to pre-train this from scratch.
So for this intermediate projection layer to the Lego space, are you reusing the hat, or you're using?
Good, excellent. So if we sample here and then we send it back into the embedding, we are in trouble because we can't do end-to-end training. So we don't do that. The key observation is this one is a distribution space. It's the same dimension as the token.
Yeah.
So I just skip the tokenizer here. And so let us say that there's for dog already. There's an embedding for this cat already.
Yeah.
To weight those embeddings with this distribution, use a mixture embedding, send it.
I see.
That's what is going. That's how you're training it. So that allows end-to-end differentiability. And that's how we're able to train this at scale. All right. So now you understand what the training model is and what the inference pipeline is. So why should let's step back and let's abstract this out and see why should this be more efficient. Okay. 15 minutes left. Okay. So let's think about a two-level graphical model. Suppose where there are a bunch of leaves and some root nodes, and let's say that there are small number of root nodes compared to the leaf. If you think that, so potentially you could think of language. This is not an exact model, but this is just an abstraction. And there are a few important words, condition on which the rest of it is condition dependent. Okay. Suppose that is indeed your world model. I'm not claiming this is the correct model, but suppose this is indeed a world model. What are the implications of this? Okay. Well, anchoring then is obviously the right thing to do because it will achieve exponential reductions in sample complexity. And why? Well, if I want to learn a joint distribution x1 to x, okay. Well, if I have no graphical structure, then a decomposition will be marginal x1, x2 given x1, x3 given x1, x2, all the way up to xl given everything before. And so if you look at the parameterization count for this one, this is one parameter. This is a function of two variables. This is a function of L variables. So on an average, it's L by 2 variables, somewhere in the middle. And so you have to learn functions which are having L by 2 variables on an average. Let's look at the anchoring model. In case you believe that the world is anchored, then It's x1 given anchors times x2 given anchors is the joint distribution. Each one is just p plus 1 parameterization. It's much exponentially lower sample complexity where some exponent goes down from L to D. Okay. So if indeed there is such structure, what we are doing essentially is a two-level graphical model decomposition. That's really what anchoring model is. And you can now think about other types of models as well. This actually gives a rich architecture space to play with, depending on what kind of structure your data has. Okay, how you could supervise intermediate layers is essentially the bigger takeaway. Okay. I have 10 minutes. So let me quickly go through this for a couple of minutes. So anchoring actually also improves inference. And to understand this, let's look at this example. Suppose the world has these 3 tokens. It's just binary. So the dictionary is either 0 or 1 and just introduce mask. So in this example, this is all that they manifest. Okay, the binary. And say the world model is this, which is give a switch. If the switch is on, this light bulb lights up. If the switch is off, this light bulb lights up. Okay. So that means this world, therefore, and the switch is on 90% of the time. Let me make sure that I've said that correctly. Yeah. So this is off. When this is 1, when this one is off. Okay. So 0, 1, this is the language, this switch, this is x1, this is x2, this is x3, this is 1 hot. This 0, 1, 0 means x1 is equal to 1. This 1, 0, 0 means x2 is equal to 0. Okay, so this is the 1 hot encoding of these things. Okay, and the model of this is that this exists in one of these 2 states. The 0.9 probability is in this state, which means it is 1, 0, 0. So 1, 0, 0 is one state. And the other state is 0, 1, 1. 0, 1, 1 is the other state. This is very, very simple toy model just to illustrate what's going on. And also you can get comfortable with the notation of how a lot of people do these discrete diffusion models. State is always represented by these categorical vectors. And when you have soft things, it will become these columns. Okay. If you use a standard reverse process in this, and say the network you have learned is perfect, your theta parameterization is that it's powerful enough to learn the ground truth. What will it do? Let's look at the inference posterior of, suppose that at some time t, all 3 are masks, meaning this state here is 1, 1, 1 in these parts. It's 0, 0, 1, 0, 0, 1, 0, 0, 1. That's the state at some point. And you ask what happens in the next time step. You can go through the calculations and you can get the next state matrix as the following. I'm just going to focus on one column. This is for this particular switch, x2. It says with probability 0.45, it is 0. At 0.05, it's 1. At 0.5, it's masked. Okay. Makes sense. Because 90% of the time it's here. So given that if you're putting 50% of the weight for mask for not being confident, the rest should be correctly proportioned between these 2. So this model has indeed learned correctly, and this is what the posterior is. And so now if you ask, given this, what's the probability to sample M0M? Okay. Remember, what you'd like to sample is 1, 0, 0. So this is something consistent. Then the probability would be 0.112. If you go to the anchoring model, what anchoring essentially does, in this case, the anchor is equal to 0. And once you're anchored, it pushes much more mass into the anchor. And so inference posterior increases. So it pushes it stronger towards the maximum likelihood sequence. That's essentially what it does in inference. Okay? That there's a higher likelihood of computing ML sequences because you're reducing uncertainty from everything else. That's essentially what anchoring it again fits in with this sort of the qualitative story I said earlier. This quantitatively, you're seeing what's going on. Okay? And in terms of practice, we have trained this model with our LM1B and OpenWebText. So this we trained the model took about, I don't know, we spent about 200,000 SUs on this to train this model. So at UT, we have a GH200 cluster of about 600 nodes. And this was instrumental in sort of training these kinds of things. So this was so we trained. So the biggest models with 500 billion tokens, and ADLM is our model, is it beat every other sort of diffusion model at this scale. But what I want to sort of few things I want to highlight are that even when compared to sort of autoregressive models of the same scale, it achieves sort of it's able to sort of match it and outperform it in a few cases, in a few data sets, which is first time actually a diffusion model is able to do some of these kinds of things. In particular, one thing that's interesting is the Morse score. So Morse score judges human. It's a good score in the sense it judges human-like quality of text. Okay, so if you can match entropy roughly the same and you get improvements in Morse score, that's actually a very positive signal. What we are able to see is the following: with an autoregressive model at the same scale with 1024 steps, the Morse score is 0.76. The ADL with double the amount of compute still is able to get 0.788. Is able to actually match. Yes, this is double the compute with an AR, but it is the first time that a diffusion model is able to get a Morse score compared to AR at any scale. And this is hopes that as you scale things up, you're going to get parallel decoding and much faster improvements in performance. It also, another interesting number is the following: that if you look at anchored model versus the state-of-the-art masking model, essentially we are getting a fourfold improvement in number of steps required. From 1020, if you look at the 1024 number of steps versus 4096 steps, the numbers are, that's where the numbers are comparable. So essentially, this notion of supervising latents is actually a powerful thing, and it matches intuition that you want to go through this information bottleneck of what you think is important if you're able to supervise it and then use that to predict everything else, even those which are masked. So this is, I have about 5 minutes left. Okay. So far I've talked to diffusion models. If you think about it, this idea of anchoring could potentially be used in an autoregressive model as well. So we can either train an autoregressive model from scratch to have anchoring, or you can do for chain of thought, you can do some supervised fine tuning. I'll focus on the supervised fine tuning in the interest of time and talk about some sort of new emergent look ahead planning properties. Okay? So I just want to quickly talk about anchored chain of thought in an autoregressive model. How will you do an autoregressive model in this sense? So this anchor transformer with causal attention is your base model, whatever your standard transform models. So look at the embeddings, the logics. Before you sample, just look at the logics it generates. That's what you'll think of as the anchor layer. Okay? This is the embeddings. These are that particular layer. And then you have a language model head, which has no attention. Okay, maybe it is an MLP or some very lightweight model. So these are the additional parameters you're putting in here. And you supervise with chain of thought in the following. So first, you do the training. So the question is, Janet's duck lays 16 eggs per day. She eats 3 for breakfast, blah, blah, blah. How much in dollars does she make every day at the farmer's market? So this is the context that you're adding into the model. Now, what is the supervision? If you are doing a chain of thought, standard chain of thought supervision, you take a thought sequence, which is 16 minus 3 minus 4 equals 9. 9 times 2 is 18. Begin reasoning, end of reasoning, supervise over that, and fine tune. But for the anchoring model, you'll also put a begin anchor, end of anchors, and extract few anchors. Suppose we allow only 2 anchors in the example. Take the first 2 digits and put that. And then supervise and train this end to end. So this is SFT. And now during inference, what you do is, now you're feeding this sequence in, and for the anchors, you don't go all the way to decoding. You take the intermediate layer and feed the embedding itself directly in here. Whereas for the rest of it, it's the actual tokens code. Okay? So this is the way the inference pipeline works. And something interesting to see here is the following. So I give you roughly the process. The same question, if you look at the chain of thought, it decided that 16 minus 3 minus 4 is 9. 9 times 2 is 18. If you look at that reasoning line, it is left to right. 16 of the first number, minus 3, then she eats, then bakes muffins with her friends every day with 4. So 16 minus 3 minus 4, and then multiplies by, it actually evaluates that, minus 9, and then multiplies 9 times 2 is 18. Whereas, even though the anchored model was trained with such sequences, the result it's actually generating is very different because it's actually able to parallelly reason. It's basically saying first 3 + 4 is 7. So it's not going in causal order. It is first deciding 3 + 4 is 7. 16 - 7 is 9. 9 times 2 is 18. So it's doing a different order, which is an emergent property, which is not expected because you trained it using a different sequence. And this is because of bidirectional, because it is focusing on these anchors, it's able to use that ahead of time to sort of think what should be important and then reason with that. And even though here we have shown no new functionality, I mean, finally both of them give the number 18 as the answer. But this is exciting to me because this is showing sort of a lookalike planning behavior, which might be useful in many other applications. And we are indeed exploring this aspect. And if you look at downstream evaluations, if you take anchoring and put it on sort of and compare it to sort of things like chain of thought or coconut or things like that, you can see sort of improved performance over these baselines. I shown you only the math. You can look at sort of logical reasoning, you have with cross QA and things like that. So we have done some other experiments. They're all in the paper. So the point I want to highlight is this notion of anchoring gives us sort of information smoothing, and essentially by reasoning, supervised latent reasoning through these soft anchor tokens. And I think this is going to be powerful for many applications. Some of this work in images is in collaboration with Google research folks, and hopefully we'll move forward with that in production. Thank you.
I think we have time for few questions. Yes.
So a lot of this is contingent on being able to find those indications that are ranked. So, how reliable is that?
Excellent. I think that's a really interesting area. I'll tell you what we did here. We simply did low frequency words are as anchors. It seems to work already better than baseline. But this is the best set of anchors so you could do various things. You could pre-process. It's computationally expensive, what I'm going to suggest. You could hold out and condition it. You could automate such a process, but this is not going to scale. Or you could try to train a language model to actually try to predict anchors first as a pre-processing. This is something that may scale if you do this correctly, and this is something we are talking to friends at.
So the thinking is that you could come up with like good heuristics to find the initial anchor, and then
exactly, and this will be domain specific. So if you have domain specific knowledge, then, for example, verbs and nouns is really good as anchors. We have seen in experiments for all the sort of logical reasoning. But you see the best set of anchors, that's not clear at all. So how to find good anchors in a systematic manner, I think is an open. Yeah.
Sure. So when you is anchor prediction, you don't know which word, how many words are anchored, right? So and for training, you have like super on the anchor.
Yes.
But at test now, how do you?
Good. So it doesn't know. So for every word, it predicts a distribution. So that's why I did. Let's look at the test time. Good, very good question. So now we can go back to a test time of okay. It's just producing the categorical distribution for everyone.
Okay.
Then we just don't going to predict anything. So maybe things it has no clue, it's just going to be uniform. That's what we are looking. Since an anchor, it's both pieces. Even the denoising transformer has learned to use this whole thing to do the next.
So the embedding, your is weighted average. These are like or like